Alright everyone, in the last lecture we had seen the first postulate of quantum mechanics, that every state of a quantum system is a unit vector of a Hilbert space. Alright, in this lecture we will learn about some basic properties, we will learn a little bit more in details of the state vectors of qubits. Okay, all right, so we know that a qubit is a two-dimensional quantum system. All right, a qubit is a two-dimensional quantum system. All right, that means that the state of a qubit is represented by a vector of two complex numbers. Okay, so in this two-dimensional vector space, if we want to form a basis set of this two-dimensional vector space, as we saw before, we can form a basis set like this. All right, we can use these two vectors as basis. Okay, so in quantum computing we have special names for these two vectors. We use the notation, we denote this vector as the zero vector. Okay, and we name this vector as the one vector. Okay, well, this naming has been done in analogy with the states of a classical bit. You see, a classical bit can be in the state 0 of or in the state 1, and a quantum bit can be, well, in the vector state 1 0 or the vector state 0 1. All right, so using this notation, how can we express the vector AB? Okay, we can write the vector AB as A times 1 0 plus B times 0 1. Or using Dirac's notation, we can write this as A0 plus B1. Okay, simple enough. And as this vector needs to be a unit vector, so we have the condition A squared modulus of A squared plus modulus of B squared equals 1. Okay, so this basis, this 0 1 basis, this has a special name in quantum computing. This is called the computational basis. Okay, all right. As we saw in our study of vector spaces, that the basis of a vector space is not unique. If this can be a basis, we can have other bases as well. In fact, consider this set. All right, I will show you two vectors. 2 1 1 and all right, so well, I have written this as this is 1 by root 2 times 1 1. That means this vector is technically 1 by root 2 times 1 by root 1 by root 2 and 1 by root 2, and this vector is 1 by root 2 minus 1 by root 2. Okay, all right. So this can also be a basis. Okay, it is actually quite easy to show that if you can express any vector AB in this form, then you can also express the same vector AB using the vectors, these two vectors, 1 1 and 1 minus 1. Okay, so we can do an example. I suppose I want to express the vector I want to express this vector. Suppose I want to express the vector 2 3 using these two numbers. Okay, what will be the coefficients? Okay, so I will just write the answer for you. Okay, if you multiply I missed a minus sign here. If you multiply them out, you can see that this will actually form the vector 3 2, not 2 3. We can easily find the solution for 3 2 if we invert them. Okay, right, this will form the vector 3 2. Okay, so I will leave it to you as an exercise that we can express any vector AB using these two vectors, 1 by root 2 1 by root 2 and 1 by root 2 minus 1 by root 2. This basis also has a special name in quantum computing. This is called the diagonal basis. Alright, this is called the diagonal basis, and these two states have special notation as well. This state is called the plus state and this state is called the minus state. Okay, so we learned about two types of basis of a qubit, the computational basis and the diagonal